Okay, great. Thank you. Thanks, Ashok. So before we start, I think this is a good point to, in fact, look for any questions if you have. I think we can address that or we can proceed further. If there are any questions, you can unmute yourself and quickly ask it. Or if it is fine, we can proceed quickly.
Yeah, so one question I asked just at the beginning in the chat, so maybe I should tell you. So the statement of Laplace that you said, so it is also not applicable for chaotic systems, is it?
No, no. Chaotic systems can occur in deterministic systems also. When we talk about chaotic systems, it doesn't mean it is not deterministic. It is only the problem with how accurately you prescribe the initial condition. If you prescribe the initial condition with infinite precision, you would definitely have a deterministic solution. Okay, you will know where you would go. That's perfectly fine. Only issue is in a chaotic system, what really happens. I mean, let me just write it out here as an aside, actually. Let's say I do have a higher dimensional state space. Let me just put it as x1, x2, x3. I do start with a certain initial condition here, and I know how it would evolve. It would evolve something like this. But let's say that I start with a small initial condition from here. Let's say this is x0, and this particular initial condition happens to be x0 star, let's say. If it is a simple linear system, what really happens is it would just go sufficiently close to the this particular x0. Okay, any two closely spaced initial condition would go sufficiently close by. But if it is a chaotic system, what it does is it would just go somewhere here. It exponentially diverges from the initial trajectory of x0. x0 and x0 star are sufficiently close by initial condition. Let me just make it clear here. x0 comma x0 star are sufficiently close ICs, initial conditions. So if you can specify your initial condition exactly, obviously it will not have any problem. Chaotic systems are deterministic. Once again, stochastic systems can also exhibit chaos. I think that's a different issue. But chaotic systems does come under the same purview. I don't think there is any issue there.
Okay.
Okay. Any other question? Okay. So let's go back to the discussion here. So once again, EC, that's the center eigenspace, unstable eigenspace, stable eigenspace, and center eigenspace. Let me just make it like M vectors also here. Okay, we'll see what is it later. Okay, so you do have a total of n of these eigenvectors, of which k is in fact the stable vectors or eigenspaces, then L unstable eigenvectors, and m of them would have zero real part of the eigenvalue, so there are vectors also there. Okay, let's put it that way for the time being. We'll come back to the discussion much bit later. Now, when we talk about a simple two-dimensional state space, that's easy to in fact understand. What I have considered here is in fact a simple dynamical system which has one equilibrium point, which is 0. That's how we have in fact linearized. After linearization, you would have 0, 0 as the only eigenvalue because it's a linear system that we're talking about, of which I do have two eigenvalues. One is positive, one is negative. Once again, as I said here, the lambda equal to 2, that's a positive lambda greater than 0, happens to be the unstable manifold, or let's say the eigenspace. That's the reason I put it as EU correspondingly. Similarly, I do have another eigendirection, which is in fact a stable manifold, which is ES correspondingly. Okay. Now let's think about it this way. If you start on any of these unstable eigenspaces, that means if you start in any of these, on any of these L eigenvectors, right? Because these are eigenvectors which are corresponding to the unstable eigenvalues, you would in fact go to infinity exponentially fast. Okay, they would just go to infinity extremely fast. Similarly, if you start your initial condition on any of these stable eigenspaces, you would converge onto the equilibrium position, I mean exponentially fast, right? It is going away along the unstable direction, coming, or let's say converging onto the equilibrium position along the stable direction. What happens with the center eigenspaces? If we start your initial condition in the center eigenspace, what really happens, we do not know. The linearized analysis wouldn't tell you anything, right? The linearized analysis, in fact, fails to tell you anything. Usual cases, people tend to think that whenever you do have real part which is in fact equal to 0 and imaginary part not equal to 0, you can directly say that this is a periodic oscillation. Not necessarily. Why? Because the linearized analysis never tells you anything when it is real part is in fact equal to 0. Okay, so that's the reason we put it as a center eigenspace in that particular sense. So this is the basic definition of a simple saddle point, and this is the phase space that we are in fact talking about. This is a saddle. Why do we call it as a saddle? I think if you just plot its integrals of motion, or let's say if you just find an integral of motion for the dynamical system that we have in fact got, you would get a surface of this particular form. Okay, so in the space x and y that I have in fact got over here, x is 1 and y equal to x dot correspondingly in that particular sense. So let me just go back. Okay, so this is in fact the saddle that we are in fact talking about. There is an unstable direction, unstable manifold, and a stable manifold correspondingly. Okay, so once again, depending on the real part of the eigenvalue, you can have different kinds of equilibrium points. This is a simple stable node that we are talking about. So once again, it has both the eigenvalues, which are in fact negative. So the eigenspace in this particular case, stable eigenspace has, okay, let me just put it across here. That makes a bit more sense. So this is 0 in this particular case, has two vectors. Okay, so one of them is 1 minus 2, comma 1 minus 1. So these are two eigenvectors. What about EU of 0? Has 0 vectors. Okay, what about EC? Has 0 vectors. Okay, that's as simple as that. Correct. So in this, for this particular example that we have in fact got, if let's make it clear here. So this is y dot equal to 0, 1, minus 2, minus 3, y. Okay. So that is in fact what we have got. So there are two eigenvectors. So which necessarily means any initial condition, it would in fact converge onto 0, 0 itself. Okay. Over here, for the saddle, any initial condition on the stable manifold would converge to 0, but any small perturbation away from that eigenspace over here, the eigenspace in this particular case, let's start an initial condition here, it would just go to infinity this way. However, sufficiently close. Okay. Only if you are on the eigenspace itself, or let's say the eigenvector itself, you will converge onto 0, 0. You will never perturb from there. I mean, you will never go away from there. Okay. But in this particular case, any initial condition would in fact converge. And once again, you can have complex eigenvalues also. So complex eigenvalues, when it can have real part, which is in fact negative, no issues with this also. It's a sink, or let's say a foci or something. So it would converge onto 0. These are the directions that is in fact showing. If alpha is greater than 0, it would in fact diverge exponentially fast outside. So the directions are shown here. When the real part is in fact equal to 0, the linear space says it is a center. Okay, the equilibrium point is a center, and any initial condition starting here, obviously it says it's Lyapunov stable. Okay, but when we talk about stability, it's usually the case that we are looking at the asymptotic stability, and the real part has to be a non-zero quantity to in fact define its stability. If it is zero, the linearized analysis doesn't say anything about it. Okay, that's a basic premise that we are in fact talking about. And that's exactly the basis on which the bifurcation theory also works, or bifurcation theory comes into picture also, where you would have a system parameter which changes, and with a change in system parameter, some of the eigenvalues would pass through the zero, or let's say the real part of that eigenvalue pass through zero. Whether it is from negative to positive or positive to negative, you would have an issue, right? That's the bifurcation that we would in fact talk about. And now let's look at the failure of the linearized analysis, linearized stability analysis. Okay, so the linearized stability analysis in this particular case, let's say that I consider a essentially nonlinear system. Okay, there is only one equilibrium point, quite easy to in fact talk about. Okay, and the the matrix, if you just find out the corresponding Jacobian matrix in this particular case, it would be in fact a singular matrix. Okay, so it would in fact be a singular matrix. Why? Just because let's say that this is z dot equal to y dot equal to minus z cube. The matrix A is in fact equal to this is 0, this is 1, this is 0, this is 0. Okay, so the matrix A would in fact be of this particular form, right? So it's a non-simple equilibrium point for that particular matter. The linearized analysis doesn't work here. Okay, the linearized analysis would just provide you with the eigenvalues which are in fact equal to zeros. Okay, so that's exactly what you would in fact have. Both eigenvalues in this particular case are zero. Just verify that, as simple as that. Okay. Now let's consider another particular case. Once again, this is linearized analysis doesn't work. Let's consider another particular case. It's a linear oscillator, but the damping is in fact non-linear over here. Okay. The damping is non-linear. Now, what really happens is the 0, 0 would have a real part of the eigenvalue being equal to 0. If you linearize this particular system, the Jacobian matrix would look something like this. Okay. So the equilibrium point, as it predicts, it's a center for us. But is it stable or unstable? Why? What is really happening is the damping is non-linear, and what really happens is as you evolve the dynamical system, you would see that the linearized system will tell you that this is a periodic oscillation, but you start at the same initial condition over here, but because of the nonlinear damping, it would just in fact converge on to 0. Right? So there is only one equilibrium position over here, which is 0, 0, and you would start with any initial condition, it would just converge, right? So in that particular sense, whenever you do end up getting 0 real part, you need to be careful about looking at the dynamical system once again, right? Don't blindly think about it as a center or let's say periodic oscillation. Not really so, because the nonlinearities could be in the damping at a higher order also. Okay, so
Can
that's
you
something
please,
that
Jay, can you please again explain this failure of linear stability?
sure, sure.
Thanks.
In which case you're talking about?
First case that you were discussing, like z double dot
Okay,
plus z cube.
right. So what I say here, this is the matrix A. Okay, let's write the Jacobian matrix here itself. Del F1 del Z, del F1 del Y, del F2 del Z, del F2 del Y. Okay, evaluated at 0, comma 0, correct? So it ends up being del F1 del Z is in fact 0. This would be 1. So this would be minus 3 Z square. So this is in fact equal to 0. If you evaluate at 0, comma 0, so this would give me 0, 1, 0, 0. Okay. Now, we need to find out the eigenvalues of this particular matrix, correct? So that would in fact be, let me just write it once again, 0, 1, 0, 0 minus lambda times 1, 0, 0, 1 is in fact equal to 0. That's the eigenvalue problem. Okay, I think CP did talk about it previously, so I'm not looking into that once again. So lambda would be in fact 0, 0 for me.
Right.
Okay.
Right.
So if it is, I'm saying that there's a center, and linearized analysis doesn't tell anything. But I can, as I showed earlier also, that this is an oscillator which has periodic oscillations only. It cannot have any other oscillations because your potential here is z power 4 by 4, right? So if you write the potential for this particular oscillator, it is z power 4 by 4. And if you write the energy, or let's say integral of motion, this becomes, let me just write it here, z dot square divided by 2 plus z power 4 by 4. Okay, this is my potential V of z. And if I write V of z, so it would in fact be a flat bottom potential. Okay, and there is only one kind of solution that it can show. There are no saddles. There is only one equilibrium point here, and it would always have a periodic oscillations.
Right.
Was it clear?
Yeah.
Okay.
Thanks.
So next, coming to the question of what is called an integral of motion. I think we spoke about three or four different invariant manifolds. Okay, one of them was an equilibrium point. The second was a periodic oscillation. The third one was an integral manifold. And the fourth one is the linearized eigenspaces. Okay, equilibrium point we did talk about. And the linearized eigenspaces, we in fact discussed it also. Okay, linearized eigenspaces are basically the eigenspaces corresponding to real part of lambda greater than 0, less than 0, equal to 0. These are linearized eigenspaces. These are the only three categories that you can have in a dynamical system, though you can't think of having anything else. It's like a trichotomy, right? A greater than 0, less than 0, equal to 0. It can't have anything else other than that. I'm talking about real part of this. Okay, that would be sufficient for complete analysis in that particular case. Periodic oscillations, I think we will talk about it when we come to the question of stability of periodic oscillations. But let's look at what is called an integral of motion. Okay. So when we talk about an integral of motion, a continuously differentiable function g, which takes n of these state variables, okay, and gives us it's a scalar function. Very simply, it's a scalar function for me. Is said to be a first integral of the system x dot equal to f of x is a constant for any solution x of t of the system. Okay. So, which necessarily means if you start with any arbitrary initial condition, it would give you a certain quantity and that quantity would remain the same. Okay. As I said, in a periodic solution, let's come to this particular case here. So x double dot plus x equal to 0. One of the integral of motion, so I'll put it as g, very similar to what we have got here, x and x dot is x dot square divided by 2 plus x square divided by 2. Okay. Now in my phase space, what I do have is x and x dot, and I start with any initial condition here, let's say. Okay, so let's say that this is x0, x dot of 0. Okay, so my value of h along my value of g would be x of 0, x dot of 0. Okay, it would be same here once again. If you evaluate g at some other location, g at x of t1, g x dot of t1 implies g of x of 0 comma x dot of 0 is equal to g of x of t1 comma x dot of t1. Okay. So that's exactly what happens. If you can find an integral of motion of this particular kind, it along that particular trajectory, you would be able to say that this is what happens. I can just write it as Ti. Okay, I could be any value. I can take any number of times for that particular matter. I just go along this particular case. Okay. Now, what really happens? How do I find out this particular function? Is there any recipe for finding it? There are no ready recipes. There is a certain orbital derivative that we can consider, but there is no way you would be able to, like in the case of an equilibrium point, if you equate it to 0, you would get an equilibrium point for sure. But there's no ready recipe that you can in fact have. Okay, but obviously there is a when we talk about the time derivative of this particular function, that is in fact equal to 0. Okay, it is not changing with time. Okay, so the total time derivative of this particular function is in fact equal to 0. That's the basic premise that we start with. Okay, but obviously when we start with this particular premise of taking the total time derivative, g is not a scalar, right? It is in fact a function which is in fact incorporating all the state variables, right? So if I have to take the derivative, I may have to take the partial derivative of g with respect to x1 into dx1 dt. This is the total time derivative of x1. x1 is my state variable correspondingly. Okay, so that's a simple way of putting things together. So del g del x1 into dx1 dt plus del g del x2 dx2 dt correspondingly. So on and so forth. You just sum up all of them. So this is what is usually called as an orbital derivative, or maybe if I'm not mistaken, I think people in fluid mechanics call it as I forgot the name actually. So the material derivative, to be honest, right? So it could be of this particular form. So what really happens is this is just a simple product of the first derivative of your g and multiplied with the vector field correspondingly. If you just put them in perspective, what really happens is I do have this vector. It's a row vector for me. dx1 dt, dx2 dt, dx3 dt, so on and so forth, multiply with a column vector, which is in fact the gradient. Okay, so the gradient of that particular function in my state space, if I just consider that, so that is in fact the second column. It is in fact a simple inner product of two vectors in this particular case. So I do end up getting a scalar value. Okay, because obviously g is in fact a scalar function, and I do take a time derivative of that, the output has to be a scalar. Nothing else can be there. There is no surprises over here. So I just do a simple multiplication. So when you look at this dx1 dt, that's in fact x dot, x2 dot, x3 dot, so on and so forth. But we do have a vector field representation, right? x1 dot is f of x1, x2, x3, so on and so forth. Similarly, x2 dot equal to f2 of x1, x2, x3, so on and so forth. In place of x1 dot, I can just replace it with f1, x2 dot with f2, so on and so forth. Okay. The product, the inner product that I'm in fact considering right now would in fact become f1, f2, f3, so on. Okay, so that's the row that I have in fact got. The column that I have in fact got happens to be del g del x1, del g del x2, del g del xn. So this is in fact equal to 0. Sorry for my handwriting actually. I'm using a new iPad, so I'm having some trouble with the smoothness of the screen actually. Okay, so this is a simple product that I have in fact got. So what I can easily do is fx transpose, because this is a vector field, we consider it to be column. I do take a transpose of that, dot product with the gradient of that particular function. The G is something that we need to find out right now. We do not know what is G. Okay, that's the function that I need to find out. And in most of the cases, energy is in fact considered, not necessarily so. Okay, so energy is not necessarily considered in a dampened system. Obviously, you will never be able to find a value of G, or you will never be able to find a function G correspondingly. Okay, what does it necessarily mean? I mean, I have taken step by step over here. It in fact means the gradient of G, which is in fact a vector in my state space, is always perpendicular to the vector field. Okay. If I find a function, okay, and I take a gradient of that, that would give me a certain direction. And that direction would in fact be perpendicular to the vector field. Okay, that's in fact what is the derivation here is in fact showing. Okay, so let me just put it across over here in this particular context. So let's say that this is x, this is x dot, and let me call this as my function g, okay, at a certain location. So if I just take a point over here, I said that I do have this as a direction, right? So I do have a certain direction. If you take the gradient of this particular function, so let's say this is g of x comma x dot, I do take the gradient of that, and this is in fact, so f1, f2, I hope I'm doing it right. Okay, so this is f1, f2 for me. So this is g. If I take the gradient of g in this particular case, what I end up getting is something like this. So this would be del g del x del g del x dot. Okay, so that would in fact be perpendicular. That's exactly what it is in fact showing for me. Okay. In a higher dimensional space, obviously, it would be a bit more complicated, but it is in fact perpendicular. That's the recipe for me. Okay, that's simple. But still, I haven't been able to find out this G. As I said, it is only possible to put it in this form, but you will never be able to find G in this case. I mean, we need to, in fact, use some intuition, use some way of, in fact, meddling with this particular equation to find out what is G. Okay, so this would in fact be a partial differential equation, right? So because a vector field is known to me, but G is not known, and I have taken derivative with respect to all the state variables, it is a partial differential equation for me. It's a single equation that I have got. I do not have any equations. I just have a single equation that needs to be satisfied such that the G is in fact an integral of motion. As I said, energy is an integral of motion. Okay, so energy happens to be an integral of motion, which in fact represents the homogeneity of time. Okay, so energy is in fact something that we talk about in the sense of classical mechanics. It in fact represents the homogeneity of time. With time, there is a certain quantity which is conserved, which is in fact the energy. So totally, it would in fact be in that particular context. And similarly, the momentum, okay, it in fact represents the homogeneity of space. Okay, it might take me some time to in fact explain what this homogeneity of space means. Let's see if we have time much later. Okay, let me not spend time on this particular case. Similarly, we can have the conservation of the angular momentum as well. There are three components of translational momentum, three components of angular momentum, and an energy. Okay, so these momentums are vector quantities. Okay, but energy is a scalar quantity for me. Okay, does every system have all these conserved quantities? No, not necessarily, right? It is obviously not possible to have all of them together, or some of them, or none of them. Okay, let me just put it here this way. Okay, let's go to this particular case actually. Okay, we'll take a simple example here. Okay, but what you can necessarily state, if you think about it, if a system has an asymptotically stable fixed point, then the system is non-conservative, which means it doesn't have a conserved quantity, which is energy. Okay, when we call some system as conservative, the integral of motion should be applicable over the whole space. Okay, let me just give you a simple example in this particular case. Okay, let's say I do have. Let's take a simple example. Okay, so x double dot plus psi x dot plus x equal to 0. So x dot equal to y dot equal to minus psi y minus x. Okay, let me just call this as f1, this is f2. So what was the recipe we had? f1, f2 into del g del x del g del y. So this is in fact equal to 0. Okay, so what is the corresponding equation I have got here? Y into del g del x minus psi y plus x del g del y is in fact equal to 0. Okay, so that is in fact the equation that I have in fact got. I need to solve for this right now. You can try whatever methodology you know for solving a partial differential equation, but you'll never be able to find a function g correspondingly. Okay, so you do not have any equilibrium, I mean any integral manifolds in this particular case. So this is a simple damped oscillator. So there is no function of, function g which satisfies this particular equation. So you will not be able to find out that. Now, this is a damped oscillator. Let me just give another case here. So let's say that I do have another system. So which is something like this. So which is on a frictionless roller. Okay. So let me just call this as 1 and 1. So this is K and C to be simple, to make it simple. Okay. So it has 2 degrees of freedom, x1 and x2. Okay. So x1 double dot plus k times x1 minus k times x2 plus c times x1 dot minus c times x2 dot equal to 0. x2 double dot plus k times x2 minus k times x1 plus c times x2 dot minus c times x1 dot is in fact equal to 0. I'm just assuming that you know how to write the equation of motion. Okay, either you can use a simple Newton's method to write this equation over here, or use Euler-Lagrange equation, Hamilton's principle. So that should be fine. Now I do have a 4-dimensional phase space in this particular case. Okay, and once again I would have the same kind of a partial differential equation for which I need to find out. Here it's a damped oscillator, a damped system correspondingly. But very interestingly, what happens is the momentum is in fact conserved in this case. Okay, the momentum is conserved, but the energy is not conserved. Okay, is it really possible? Energy is not conserved, but momentum is conserved. Just add these two equations together. What you would end up getting is x1 double dot plus x2 double dot is in fact equal to 0. Okay, what does that really mean? X1 dot plus x2 dot is equal to some constant, right? Momentum is in fact conserved in this case. The total momentum in this particular case has in fact been conserved. If you just add them together, just work it out. I think it's easy to in fact do that. So if you just add them together, you would see that x1 double dot plus x2 double dot is in fact equal to 0. The total momentum is conserved, which implies I do have x2 dot is equal to some constant. Okay, g of x1 dot and x2 dot is equal to constant, but energy is not conserved. You will never be able to find a energy equation that is in fact conserved. So what is the statement that I'm making here? The second bullet over here happens to be that the momentum is in fact restricted to only the velocities here. Okay, it's not applicable, or let's say it's not in the whole of state space or phase space correspondingly. Okay, if it has to be energy, and if you want to call the system to be conservative, then you need to find out x1 dot, x2 dot equal to some constant. Okay, that's something that you need to find out. Okay, so if it has to be in this particular form, in this case energy is not in fact conserved, so you will never be able to find a certain quantity h, or let's say a function h in this particular form. Okay, fine. So I mean, I'll just leave it as a simple example. This is a general nonlinear equation that I have in fact considered. We do use the same recipe, that is del f del x into dx dt plus del f del y. That is del f del x, del f del y are in fact the gradients, or let's say the components of the gradient vector of that function. Multiply that with the vector field, you would get a partial differential equation here. Okay. What trick I usually do, I mean, you can in fact think about it this way. I'll just try to equate del f del x to this particular term over here. Okay, I'll just try to equate these two in this particular case. Y can be in fact divided over here. So the coefficient here becomes minus c plus ex, which is in fact a function of x alone. Okay, so similarly, I would be able to do same thing on the other side also. Del f del y can be equated to the other coefficient over here. Okay, I'll try to do this so that I will get a equation in this particular form. Okay, I'll just try to manipulate it a bit. Okay, so del f del x equal to this equation. Note that f is still a function of x and y. Once you get the constant of integration after integrating the first equation, as simple as that, the first equation, the constant of integration would in fact be a function of y. Similarly, on the second part also. If you just put them together, what you end up getting is this particular integral. Okay, this integral of motion, try doing something interesting. What you do is just put it in MATLAB ODE 45, let's say. Just try to give certain initial condition and try to find out this constant value, right? As time evolves, this quantity would always be a constant. Okay, so a very simple way of in fact verifying is using the MATLAB. Okay, directly you can do it here also. I mean, you can use the same recipe for finding integral of motion for any other oscillator also. No big issue, but you should be able to check it out this way. Okay, so when I say in integral of motion, it becomes in fact a surface, and all the solutions would in fact lie on that particular surface. Okay, so that's in fact what happens. I think I would really suggest you go through this very interesting book. It's a pictorial book actually. It doesn't have any equations. It only shows through pictures the dynamical systems. Okay, a lot of interesting sketches and pictures. You would be able to easily visualize a lot of things, because most of these things are in fact geometric in nature. Okay, instead of going for the equations, if you just look at the geometry, I think you would better appreciate the whole notion of dynamical systems in that particular context. And this is an excellent book in that context actually. So it's the geometry of behavior dynamics. It's an out of print book, but it should be available in some of your libraries. There are no equations. If you are really mathematically oriented and only want to write equations, this is not the book for you. But it's a pictorial book, a comic book to be more precise in that sense. You can just have a look at it actually. Okay. Okay, so this is a simple qualitative analysis. I think you already know. We already discussed this particular part. So if you have a differential equation, and when we consider this particular idea, it has to be a conservative mechanical system, or let's say conservative system to be more precise. Okay, so when you have a conservative system, you can just split it into kinetic energy plus potential energy, which is in fact equal to 0. And when we talk about the conservativeness of the particular forcing, it has to have a certain scalar potential from which it can be derived. And the potential here obviously is a function of only the generalized coordinate, not of velocity. Okay, in a very, very general sense, I mean, in a very specific sense, I'm talking about it here. So that's the reason I say when I take gradient, I'm talking about taking gradient in the configuration space, not in the state.
I'm sorry, Jay. Actually, just can you please unmute
No,
yourself? Yeah.
sure, sure. I'll do that. Thank you. So this would in fact be the energy integral. Okay, so you can work it out from the previous recipe for finding the integral of motion also. Once again, it has a potential, it has a kinetic energy plus a potential energy, which is in fact equal to the total energy over here. Now, without even going through all the stability analysis, or let's say finding eigenvalues and eigenvectors, just looking at the potential also, you would be able to tell for a conservative system, you would be able to say if it has oscillatory solutions or it is a saddle. In a conservative system, these are the only two equilibrium points that you would be able to observe. Okay, it would be a center with zero real part of the eigenvalue, and there would be a saddle where one of the eigenvalue is positive, the other is in fact negative. So let's try to see that. Okay, so let's try looking at it in this particular context. So once you write the potential energy in this particular form, if you take the gradient of that and it in fact make it equal to 0, you would find out the fixed point of that particular system. Okay, so take the gradient of that potential energy function and you equate it to 0. If you just look back at it here, so the gradient is in fact the forcing. Okay, so the restoring force on your particular system. If the restoring force is 0, obviously you do not have any dynamics whatsoever. Okay, so that's a simple way of looking at things over here. Okay, I do take the derivative of my potential energy equated to 0. Whatever is the point I would end up getting is in fact a fixed point for me. And note that because I already a priori mentioned that this is a mechanical system, there is no velocity component. All my fixed point would be in the configuration space. I don't have to worry about the velocity. It's not a general dynamical system that I'm talking about here. Okay. Now, once you find out the fixed point, the next question is it in fact a minima or a maxima? Okay, that's a simple way of checking. You do the second derivative test over here, and if the second derivative is in fact greater than 0, then it is in fact a minimum point of the potential energy function. That is in fact a center for me. Center, obviously relating it to our previous idea that the real part of the eigenvalue would in fact be equal to 0. The imaginary part would be a non-zero quantity for that matter. And the other quantity, obviously, if it is in fact negative, is in fact a saddle and it's a maximum value. Okay. Now you can ask me what happens if it is in fact equal to 0. The second derivative is also equal to 0. You may have to go for a higher order testing. Okay, so you may have to take a third derivative, verify its positiveness or negativeness, go further, so on and so forth. But most of the cases you would be able to see what really happens in this particular scenario here itself. Just verify. I mean, so in this particular case, let's take it as a simple example. X cube equal to 0, a very simple case here. So V of x is in fact x power 4 by 4. So del V del x, I don't have to call it as del V del x here, dV dx should be sufficient in this case. So this becomes x cube. This is in fact equal to 0, which implies x equal to 0. X dot is already 0. I'm just repeating it so that you don't get confused with state space and the configuration space. Now let's take another derivative, del square V del x square is equal to 3x square. Is also equal to 0 at x equal to 0. Okay, I do not know what it says right now. let's go to the next one. Del square v, del cube v, del x cube, x equal to 0 is 6x, x equal to 0 is in fact equal to 0. 1 second. Okay, let me go for another one. Del per 4 del x4 at x equal to 0 is 6 at x equal to 0, which is 6. Okay, now I do have a positive quantity, okay, for a fourth derivative. Okay, and that necessarily means I do have a minima, or let's say a minimum of my potential energy function at x equal to 0, which necessarily means I do have a center and oscillatory solution. That's a simple way of checking. You do not have to even integrate, you do not have to do any other kind of analysis. As I said, in the previous case, when we did the linearized analysis couldn't tell anything about this particular oscillator. But if I just do a simple qualitative analysis, because I already know this is a conservative system, you can use the same idea. I'm not, in fact, going through complete analysis here or taking a lot more examples. So this is a simple way of, in fact, verifying the conservativeness of the system also. Okay, so energy is conserved. So I will be able to look at the potential energy and be able to tell that there is an oscillatory solution. That's a simple check that you can, in fact. Now, what happens if I say x double dot minus x cube equal to 0? Okay, just verify this. Okay, so what really happens in this case is del 4 uh, del 4v del x4 at x equal to 0. Still x equal to 0 is an equilibrium point. 6 at x equal to 0, this is minus 6. Okay, it's in fact a maximum point. Okay, so it is in fact inverted. Your same potential well that we had got here. Okay, let me, has got inverted in that particular case. Okay, so this is x, this is a v of x, so on and so forth. Okay, so obviously you can verify this, the stability of this equilibrium point for conservative mechanical system. I mean, these are some very simple cases. I think I'll leave it aside. I think it doesn't make sense spending time on this. You can write the potential energy, and obviously you would be able to look at its contours. It has a flat bottom. I mean, it has a minimum at x equal to 0, y equal to 0 in this particular case, and it has oscillatory solutions. This is the energy contours that I'm talking about. So you start at some initial condition here, it would just keep on oscillating from here to here at the same energy level. Because it's a conservative system, it could be somewhere here. I start somewhere in this particular point, it just keeps oscillating, right? So obviously it has velocity. It is not an equilibrium point that I'm starting. If I start my system over here, obviously it would stay there. No big issue. I think you have already seen that. So similarly, several other potentials can be looked into. And once again, you don't have to do any linearized analysis. Looking at the potential, you'd be able to say how the energy contour in fact looks like. This is a very intuitive way of in fact looking at the dynamical system. Because what usually happens is every time you need to scramble around for a pen and a paper to do the analysis. But looking at the equation, okay, you should be able to at least predict it has oscillatory solutions about a certain point or not. I mean, going through the analysis is good, but at least intuitively you should be able to have a feel of what this in fact looks like. This is a simple Duffing oscillator, right? It's a Duffing oscillator. I do not have 1/6 here because I have expanded my sign of x over here. I do not have 1/6, but obviously characteristically they are similar. Okay, there are two saddle points over here, two maximas, and there is one minima at this particular point. These are global maximas for me. Okay, so these are heteroclinic orbits, homoclinic orbit. I think if you just flip the sign of that particular function, x double dot minus x plus x cube, you do flip the states. I think that's exactly what you see over here. Homoclinic orbit is in fact an orbit which connects an equilibrium point with itself. The equilibrium point that we are talking about happens to be a saddle. Okay, saddle obviously has two directions. One is an unstable direction and a stable direction. So the trajectory starts along the unstable direction and comes back to the stable direction. Okay, so this is the unstable direction. It is moving away from here, and this happens to be my stable direction. This comes back over here. Okay, that's a simple homoclinic orbit that we are in fact interested in. I think we will talk about that hopefully if we go up to Sine-Gordon equation, where we once again look into the envelope solitons, and you do have this homoclinic orbit coming into picture in the effective potential. Okay? I have arbitrarily taken a certain potential. It doesn't correspond to any mechanical system that I know of, at least, just to give you a glimpse of how it would in fact look like the phase portrait. Each of these minimum points, the local minimums, it's not global minimum. I'm not claiming that they are global actually. So the global minimum points correspond to closed orbits around it. So which are centers or oscillatory solutions. Because there is no damping, I can peacefully say that they have only oscillatory solutions. They will not lead to any nonlinear damping that I'm including. Okay, so because it is conservative, I am just assured that there are only oscillatory solutions and maybe saddles in this particular sense. Okay, I can just fix up it, look at the potential energy, and I would be able to say how the energy contour in fact looks like. Okay, so the same energy contour, I did consider the same, let's say the pendulum over here. I added a certain amount of damping. Okay, now the the phase portrait looks quite similar. Okay, this is exactly what I said previously. If it is in fact a hyperbolic equilibrium point, so these are hyperbolic equilibrium points, right? So these are saddles, which are hyperbolic equilibrium points because the real part of eigenvalues are not equal to 0. So these are saddles. Close to that, the nonlinear solutions would in fact match with the linearized counterparts. But when you look at 0, 0 over here, when it is undamped, it is periodic oscillations. When it is damped, it becomes a spiral, inward spiral over here. Okay, the shaded region is what is usually called the basin of attraction for this. Okay, each equilibrium point, mathematically there are infinitely many equilibrium points. Physically, they are the same for us. Mathematically, if you just keep on going, each of these equilibrium points has a basin of attraction. Okay, this is a non-conservative system. Okay, because I'm just superimposing the non-conservativeness on the conservative part of the system so that you will know there is a certain region called the basin of attraction in this particular case. Okay. Okay, so this is something that you would be able to visualize also. So this is the energy contour over here, and I start with a certain initial condition over here, and I just converge on to this. So these are the energy contours below. This is the total energy surface for me. Okay, so this could in fact be, let's say, G of x dot in this particular case. Okay, so corresponding to a certain energy. At each energy level, you would be able to say that I do have a certain energy. Because it is damped, obviously it would stay on that surface, but it will not stay at the same energy level. Okay, the energy keeps on decreasing for it, right? So as it damps. So that's a simple representation that we can in fact think about. Now, we are looking at periodic solutions. Okay, so most dynamical systems, I mean mechanical systems, we are interested in harmonic oscillations or periodic solutions. And obviously, whenever we generate or whenever we find out that particular periodic solution, we would want to study its stability as well. Okay, in a similar way, what we did with equilibrium points, we would want to study the stability of the periodic solutions. Once again, the notion of stability here is also the same thing. Okay, it's not any different. It's the same Lyapunov stable or asymptotically stable asymptotically stable periodic solutions that we would be in fact looking into. Let's start with a very simple non-autonomous dynamical system z dot equal to g of t comma z, because obviously even autonomous systems have periodic solutions, but let's consider a bit more general dynamical system over here. And we do have a certain periodic solution, psi of t plus capital T is psi of t. Okay, t is in fact finite. That's in fact the time period of the oscillation here. Okay, so the periodic solution is Lyapunov stable for each t0. That's the initial point that I'm in fact talking about, initial time instant. And epsilon greater than 0, we can find delta such that this particular equation is in fact satisfied. I start at a certain initial position over here, right? And as I evolve further, okay, as I evolve, that is in fact the periodic solution that I'm in fact talking about, if it is within this particular delta over here, and as time evolves, what happens is it has to be within this particular epsilon circle. Okay. Now we spoke about this in the context of equilibrium points. Let me just put it across here. So this is X or Z1, Z2, and I do have a periodic solution. Okay, so this is a periodic solution that I have got. Psi of t is psi of t plus capital T. Okay, I start at a certain location over here. Okay, so that's my initial point that I'm in fact looking into. So let me just call this as psi of t0. Okay, now I give a small perturbation to this particular part here. Okay, so this is radius delta. Okay, now I will be able to say after a certain time duration, so this is epsilon for me. Okay, if I start within that region delta, so which is in fact this particular region, I am just saying that if it has to be Lyapunov stable, it has to be at after certain time duration. Obviously, t greater than t0, I need to make sure that the trajectory would in fact lie within this particular region. Okay, so that's an epsilon value. Okay, in the case of equilibrium point, you start at that particular position and you stay there. I mean, you do not evolve outside that. But here, what is really happening is it is in fact going through one full circle, but it has to reach within that particular epsilon. If it goes beyond that epsilon, obviously it is not Lyapunov stable. Epsilon and delta are in fact given to us. Okay, now a more restrictive definition in this particular case is asymptotically stable. Okay, I start with the same set of initial condition, but it has to converge on to the periodic solution itself as t tends to infinity. Once again, this is a limiting case that we are talking about. Can we think about a periodic solution which is asymptotically stable? You can think of something like a limit cycle oscillation. Okay, a limit cycle oscillation is an asymptotically stable periodic solution. Okay, why? Just because, let me start somewhere here. I go sufficiently close here. I always converge on to my equilibrium, I mean periodic oscillation. I start somewhere outside, I converge on. Okay, so I do not have any problem here with asymptotic stability. So the limit cycle oscillation in this particular case, this is a LC for a van der Pol. Okay, so that's a simple limit cycle for a van der Pol oscillator, and I would be able to say that this is asymptotically stable. You can easily verify that. We'll talk about that stability a bit later. Now, in a more general sense, how do I check for stability? So similar to what we did for the case of equilibrium points, we linearized it, right? Isn't it? We linearized very close to that equilibrium point, and what we ended up getting is a linearized equation, and we studied the eigenvalues of that linearized equation, and we, depending on the magnitude, or let's say depending on the real part of the eigenvalue, we said it is stable or unstable correspondingly. Okay. On similar lines, we will in fact consider this particular system over here. Okay. And I'm just taking it to be a mechanical system for that particular matter. Once again, I do have m configuration space over here. Okay. Obviously, the state space would be 2 times m correspondingly. Okay. And I do have a periodic solution. Okay. So for the periodic solution, what I do add a small perturbation, which is phi of t plus eta. Eta is in fact my perturbation over here. Okay. So phi and eta are in Rm because these are n quantities that I'm in fact providing for them. Okay. So that's a simple representation that I'm in fact using. I'm just making it precise so that this makes complete sense over here. Okay. Now, if I just substitute this perturbation into my equation of motion here, okay, so phi of t is in fact function of time. Previously, the x star, that was in fact an equilibrium point, the time derivative of x star was in fact equal to 0, right? Obviously, it's a point, it is not evolving, right? F of x was in fact equal to 0 at that particular point, okay? But here, what I have got is phi double dot plus eta double dot. The perturbation is also time varying. As time evolves, if it converges on to the periodic solution itself, we will call it as asymptotically stable equilibrium point. If it in fact diverges, it is asymptotically unstable. If it stays wherever it is, it doesn't change its position, obviously it is in fact neutrally stable. Or let's say it would in fact be a center for us. Okay. So if you think about something like a simple harmonic oscillator, every periodic solution would in fact be Lyapunov stable. Okay, because if you have something like let's say x double dot plus x equal to 0, what I end up getting here is, let's say, x and x dot. So let's say that there is a periodic solution. I start with any initial condition close by, it would also be a periodic solution. Okay. So similarly, if I start with any other initial condition, obviously close to that periodic oscillation, it would also be a periodic oscillation. Okay. So that would in fact lead to what is called the Lyapunov stable periodic solution, right? But not always the case over here. So what we do, once again, the Taylor series does come to our rescue. I think CP did in fact talk about that in the other lecture, so I'm not going through. I think he relieved me of a lot of let's say a lot of time in fact. So what happens is, this is in fact a simple Taylor series expansion that I have in fact done. The basic solution is phi and phi dot. Phi is known, phi dot is known correspondingly. I do a Taylor series expansion, right? And this in fact is in fact equal to 0. Why? Because phi is in fact a periodic solution of this dynamical system. So this term should in fact be equal to 0 because of the periodicity. Now, whatever is left over happens to be the variational equation. I'm neglecting all the terms which are of higher order. I don't have to worry about them. I mean, this is exactly what the linearization we did in the for the equilibrium point also. Okay, so this particular equation is in fact, let me remove this here. So this, sorry, one second. So this particular equation is what is called the variational equation. Okay, so the variational equation has coefficients over here, which is in fact time varying coefficients. Why? Because f of phi comma phi dot, I mean, I'm taking the derivative, just read this particular statement here. When I say del f, del y, I do take the derivative, then impose that particular periodic solutions over here, not before that, because before that it doesn't make any sense. I do take the derivative and I then impose the periodic condition over here, or let's say periodic solution over here. So what I end up getting in this particular case is the coefficients which are in fact time varying coefficients. Okay, so there is acceleration term or inertia term, there is a restoring force term, there is a damping term also. Okay, because of the velocity that I have got, the coefficient could be positive, negative, we really do not know as of now, but I do have a variational equation to the first order. Now, what is so interesting here? Because I did in fact did the variational equation over here. As time evolves now, if eta in fact goes to 0, right? As time evolves, then I can safely say that my periodic solution phi is in fact stable or asymptotically stable. If in case eta is in fact a constant value, or let's say it is oscillatory, within a certain bound, if it is oscillatory, then obviously I can easily say that my periodic solution is stable, at least Lyapunov stable for me. Okay. Now, if eta in fact diverges as time increases, obviously I would say that my periodic solution is in fact unstable. Okay. So that's the basic premise. So we have reduced the question of stability of periodic solution to a second order equation over here. Okay, but note that they have time varying coefficients. They are not constant coefficients. If it was constant coefficient, I would have used the same idea that we did previously, and I would have found out the eigenvalues, and I would have said if real part of the eigenvalue is positive, it is unstable. If it is negative, it is stable. If it is equal to 0, I would call this as something like a center. Okay, so that's as simple as that. But here they are time varying coefficients. That's exactly where we would talk about something called Hill's equation or Matthew equation and what is called the Floquet theory of analysis. Okay, uh, I mean, before going to that, I think let's make a simple reduction here. I think this is the form of equation, right? I'm just writing it in this particular simplified form over here. So this is same as, so let me just write it here. Eta double dot plus del f del y evaluated at phi comma phi dot into eta plus del f del y dot phi comma phi dot eta dot. So this is in fact equal to 0, and this is being written in this simplified form: x double dot plus p1 of t. Sorry, I think I should take this as p2 of t into x plus p1 of t into x dot, in fact equal to 0. And because phi and phi dot are in fact periodic functions, obviously the coefficients are also periodic. So p1 comma 2 is p1 comma 2 of t plus capital T. Okay, so they are periodic in nature. I'm just reducing it into a simple problem where I just have 1 degree of freedom here. Let's not worry about making it more complicated. It can be obviously extended to any higher dimensions also. Okay, we do not have to worry about that. Now, a simple transformation, I think that's this would be explanatory for you. I think I will not spend time on this. So a simple transformation would convert this damped system, okay, to an undamped system of this particular form. Okay, and this conversion leads to what is called the celebrated Hill's equation. Okay, so most of you might in fact know what is a Hill's equation. It is in fact a oscillator with time varying coefficient here. Okay, so this is the time varying coefficient that I have got, and the time varying is not arbitrary time varying, which is in fact periodic time variation. It is not arbitrary time variation. So that's in fact the Hill's equation for us. So this is the transformation that we have got. A more specific case of Hill's equation is what is called the Matthew equation, okay, where P of t is represented in this particular form, which is delta plus 2 epsilon times cosine of 2t. I mean, it could be cosine of t or anything, but what is relevant here is there is a factor delta which is added inside. There is a mean value, okay? So P of t is in fact right now, let me put it here this way. So this is time and P of t would be somewhere here. Okay, so this is delta. Okay, so delta plus there is some oscillation here depending on the value of epsilon. Okay, so that's 2 epsilon for me, 2 epsilon. Okay, so the function here I'm writing is P of t for you. Okay, so depending on the value of delta, I think it just keeps on moving positive or negative, and that's what is called the Matthew equation. Okay. So that's William Hill, and as you can see, books have been written on this Hill's equation, and by that you should be able to see what is the relevance of this kind of equation. I think many dynamical systems we end up getting equations where it is time varying, and time varying more often with periodic time variation, because most mechanical systems that we talk about have some part which is oscillatory in nature. So the coefficient becomes periodic time variation. That's where Hill's equation, Hill's analysis, or let's say what we call as the Floquet theory come into picture. Okay? These are some works. I think this would be quite interesting. Some of them are in French, actually. These I just put it as a reminder of what people have done way back. I think what we are understanding now, or what we are trying to understand, people have worked on it sufficiently way back. Okay, so this is the work by Floquet. I think he proposed that particular methodology, a very interesting way of, in fact, finding the stability of periodic solutions, or finding the stability or in the case of Matthew equation correspondingly. So this is the work by Matthew. Okay, this is a book, in fact, Dynamic Analytic. So you can just have a look at it if someone has a what do you call translated version. It's quite interesting to historically see what they did. You can see the date here. It is 1878. Okay, still we find it quite relevant and quite interesting to study what really goes in here. Okay, I'll not spend time on this part. I think it would take me more time here. And obviously, it's not the only way you can come up with the Hill's equation, or let's say the Matthew equation. As I said earlier, when you talk about parametric excitation of a simple pendulum, you end up getting once again a Matthew equation or a general form of Hill's equation. Okay. If I just remove the external forcing, the horizontal motion, and just have only the vertical motion, what I end up getting, if it is periodically oscillated, so what I end up getting is in fact the Matthew equation correspondingly. Okay, so that's a simple representation. As I said, you can arrive at this Matthew equation from the context of stability of periodic solutions. That's one way of approaching this. Or you can consider this as a oscillatory system where there is parametric excitation. Parametric excitation basically means there is a certain parameter in your system which is time varying, and that particular excitation here is in fact periodic for simple and obvious reasons here. Okay? So once again, this is linear system. Okay, after linearizing it, this is a simple linear system. But still, of all the nonlinear dynamics that we are talking about, why are we really worried about a linear system? Because we are trying to understand the stability of periodic oscillations. Okay, though it is linear, the linearized analysis previously that we have in fact considered may not really work. Okay, we will see some interesting responses also over here. Let me just try if I can run it over here. So I hope you can see. This is a simple MATLAB code that I just have considered here. Let me just, I have just entered this Matthew equation over here with the delta equal to 1. Okay, so let me just run this code for an arbitrary value here. So it might take a few seconds. Okay, so it has some very bizarre kind of response, right? I'm just showing only the displacement over here, okay, as a time series. Now let me just make this frequency equal to 2. So delta is in fact equal to 1. The frequency of parametric excitation is in fact equal to 2. Let's see what happens. It has all the way gone to infinity. Okay, so it has in fact gone unbounded. Okay, so let's make the frequency of oscillation equal to unity. So the frequency of excitation and the linearized natural frequency. When I say linearized natural frequency, I'm talking about root delta. Okay, so the root delta would be my linearized natural frequency. When both this excitation frequency and the linearized natural frequency are same, it is going unbounded. But when you make the excitation frequency, let's say twice, the rate of increase is much, much higher. You see the order of magnitude that you are seeing here is 10 power 5. Previously, it was just going to about 200 or 300. Okay, so that's exactly where our analysis comes into picture, and how do we, for what values of delta you would have stable oscillations, unstable oscillations, or stationary solutions, so on and so forth. That's something that we would in fact look into in the Floquet analysis. Okay. Now, this is a simple experiment that we did in the lab over here. What we have done is, you can consider it as a simple compound pendulum. I mean, not simple compound pendulum, a compound pendulum. We have mounted it on a vibration exciter over here, modal exciter, and we are trying to see when the oscillation starts growing sufficiently large. Okay, on the left plot, what you see here is whenever it is in the vertical position, obviously it was an equilibrium position. It shouldn't have moved. The student gave a small perturbation. What you see here is it has started growing rapidly. Okay, it will not go to infinity, or it will not start rotating. Why? Because it depends on the parameters also. Okay, but obviously as the amplitude keeps increasing, the nonlinearities start affecting the system. Our analysis that we are doing is linear, but as it grows, obviously the nonlinearities come into play. Okay, that's the reason it would be still bounded. It will not go to infinity, or for certain parameters you can take it for a full rotation, take it for a ride, if you want to call it that way. You can rotate. On the other hand, the vertical position can be stabilized. The theta equal to 0, which was inherently stable, can be made unstable. Similarly, the vertical position, which is inherently unstable in the absence of parametric excitation, can be made stable. There was a small issue with the positioning, so that's the reason there is a small angle, but you can make it vertically upwards like this. Okay, so you can easily do that. So that is exactly what we would in fact look into. Okay, I will in fact not make the complete analysis. I don't think I do have that amount of time. I think I have already running short of time actually. So let's start with the basic premise of the analysis over here, why we are interested and how it works. Okay, let's consider a simple dynamical system. Okay, where all the time previously we considered the coefficient to be just a matrix, which was in fact a constant value. So this is in fact a matrix. Okay, to be precise. Fine. So this is in fact a matrix. Previously, in the case of equilibrium point, it was in fact a constant matrix. Okay, it was a Jacobian matrix also. Now, instead of the constant matrix, now we have a matrix which is in fact time varying. And is it arbitrarily time varying? Not really, isn't it? So we have already seen that it is in fact periodic time varying, and it's an n cross n matrix once again. Okay, I'm considering a first order equation. Obviously, I can reduce my Matthew equation over here. Let's or Hill's equation. So let me just take a different route here. So let's say that this was b of t into y is in fact equal to 0. B of t is b of t plus capital T. Okay, y is r, that is a single degree of freedom. Is what I'm talking about right now. So I'll write this as y dot equal to z, z dot equal to minus b of t into y. Okay, so can I now put it in the same form? So y dot z dot is in fact equal to 0, 1 minus b of t, 0, y and z. As simple as that. Okay. Now, this is what I am just calling this as a of t into x. Okay. My a of t matrix, a of t, is in fact same as what I had got here, 0 minus b of t, 0. Does it satisfy my assumption that a of t is in fact equal to a of t plus t? Yes, it has to satisfy. No big issue, right? You can easily verify that. So let me just write it clearly. This is b of t. Okay. So obviously the coefficient matrix is in fact periodic time varying. Okay. So that's the initial equation that I have in fact considered. Now, before going to the Floquet analysis, let's try to understand the basic analysis itself. Okay, let's make it a bit more simpler. Let me just consider a first order equation. Okay, so phi is in R, which means I just have only one state variable, and the coefficient here is in fact time varying. Okay, periodic time variation. Once again, it's a simple scalar function for me. It's not a matrix anymore, because psi or phi that we have got is in fact real, a real value with R1 and correspondingly. So I do have this. Very simple. I can do a simple integration here, isn't it? I can just do an integration here with a constant of integration. It in fact becomes exponential 0 to t at dt correspondingly. Okay, you can do this integration. There is no issue in doing this integration. If it was in fact a was in fact a constant, you would have got something similar, right? It would have been e power at correspondingly, right? If a was in fact a constant, not time varying, you would have got phi 0 into e power at correspondingly. Now, because it is in fact time varying, I may just have to do this integration over here. Now, understandably, a of t is in fact periodic, and once again I'm referring back to CP Prakash, when you did this delay differential equation. The a of t, if it is periodic, obviously I can do a Fourier series expansion. Okay. A of t, should it in fact be a continuous function? Not really. It need not be a continuous function also. Why? Because let me just, should it be smooth? Not even really. Okay. So let's say this is t, this is a of t. Can I have a function of this particular form? Yes, I can have it. Or let's say that I do have a sawtooth. Okay. Can I have this as a function? Yes, you can peacefully do that. You just need to have a time period, right? This is capital T. So this is capital T in the other case. Okay. So can I have something like, let's say, I'll take a different color. Can I have variation something like this? Why not? Okay. So all of them are periodic. I can just do Fourier series expansion for each one of them. Okay, the number of terms that you might have to take differs, but doesn't matter for us, right? So it is just a matter of considering the Fourier series in this particular case because A of t is periodic. Okay, I do a simple Fourier series expansion. You know how you have got this. One thing that you need to note, I mean, you don't have to remember this particular what do you call relation also. One thing that you need to remember is all these cosine functions and their higher harmonics, cosine and sine functions, are in fact linearly independent functions in the domain that we are in fact talking about, in the time domain that we are talking about. So that is 0 to capital T for that particular matter here. And they are linearly independent, first thing, and they are orthogonal also. Okay, need not be, I don't have to restrict it to orthonormal, but they are orthogonal also. So the orthogonality and the linear independence, obviously, I mean, the functions which we are talking about here are orthogonal, so it implicitly means it is linearly independent also. Okay, so but not all linearly independent functions are orthogonal. That's something that you need to remind yourself. So these are orthogonal functions, so I would be able to expand any of them. Okay, so if I do a simple expansion of this particular term over here, and once I do an integration from 0 to capital T, let's say that I would want to find what is phi at capital T, that is one time period of this particular coefficient here. Okay, if I do an integration of all the terms here, all the harmonics would in fact go to 0 because they are periodic with capital T. Though the frequency might be different, but their time period would in fact match with the capital T here. Okay, all the higher terms would in fact go to 0. Only term that would in fact not vanish is in fact the constant term over here. Okay, so the constant term k0 divided by 2, that's the coefficient integrated over 0 to capital T. Phi 0 is in fact the initial condition. Phi of capital T is in fact what you have got. Okay, that's a simple expansion that we did and do an integration here. Now, what really happens here? That's something interesting that we need to see. Okay, so let me just put it this way. So phi of capital T is phi of 0 e power k0 by 2 into t. Okay, so this is in fact what I have got. Okay, now let's say I would want to find 2t. Okay, so if I want to find it up till 2t, what would that be? Phi of 0 e power 2 times k0 by 2 into capital T. So phi of nt is phi of 0 e power n k0 by 2 into capital T. Is it simple? I think you can do it recursively. No big issue. So n is an integer. Okay, I'm just looking at my response only at that particular time instant, 0, capital T, 2t, 3t, nt correspondingly. Okay, now if you just look at this particular solution, when is the solution going unbounded, or when is it in fact being decaying? It's as simple as that. If k0 is in fact positive quantity, the solution goes unbounded. Okay, though we are looking at only t equal to capital T, 2t, so on and so forth, I can easily assure myself that as time increases, the response goes unbounded for sure if k0 is positive. What happens if k0 is negative? It would decay to 0. Okay, so it would just decay down to 0 in this particular context. What happens if k0 is equal to 0? It is in fact the same value, right? So if k0 is less than 0, phi of n capital T tends to 0, right? Phi 0 is a finite value, and whatever is exponential, it would decay to 0 as n tends to infinity. Because n is the integer value that I'm considering, I'm not taking a real time here. So that's a discrete time dynamical system also in some sense. Okay, so k0 greater than 0, phi of n capital T tends to infinity as n tends to infinity. Okay. So K0 is in fact equal to 0. Phi of nt is equal to phi 0 itself as n tends to infinity. Okay. That's the simple premise. Okay. That's the whole idea of, let's say, talking about Floquet theory, anything. It is just this particular core idea. Okay. Did we do something different here? No, it is nothing different. If you just look at the whole notion, if you had considered, let me say that, let's say psi dot equal to a times psi. Okay, so a is constant. Okay, and psi is real. Okay, psi of t was in fact e power. So sorry, it's not psi 0 into e power at, right, is your solution. If a is a constant, this is your solution. Okay, so what would happen? A less than 0, c of t tends to 0 as t tends to infinity. A of 0 greater than 0, c of psi of t tends to infinity as t tends to infinity. A is equal to 0, psi of t is equal to psi 0 as t tends to infinity. Okay, a very simple approach, or very simple correlation that we are in fact making here. Okay, but what is so different from here to here? Here, time is real, is what we have considered. Here, n is an integer. Okay, what is the symbol for integer? Z, right? So n is an integer. I am just looking at the response at particular time instance. So that's the reason the discrete discrete time dynamical system that we are in fact talking about. So what it boils down to is, whatever might be the time varying function, if you say the constant part of your Fourier series expansion would decide if it is stable or unstable, it is growing unbounded or bounded. Okay, so that's the basic idea. That's the basic premise. Think, I'm not sure how many of you have read this particular book. It's Lamberto Cesari, a classical book on asymptotic behavior. A very interesting book, maybe out of print once again. Do have a look at it in your libraries. I think it's a classical work on asymptotic analysis and these approaches actually. Okay. Now, obviously, we restricted ourselves, starting with the simple case of 1 degree of freedom or 1-dimensional state space. Obviously, that is not sufficient for us. Okay, that was too simple. But the idea remains the same. No change in the idea over here. It's only the complexity, or let's say the methodology that we choose is a bit different. That's it. Okay, let's go back to the same problem that we started off with. I think this is exactly the problem. Okay, so X is in n-dimensional space and A is in fact a square matrix. I'm starting with the same idea. Okay, now what we do over here is, in fact, let's say that I do want to just note that this is no time delay here, not getting into the realm of what CP was talking about. This is no time delay in this case. It is just that I'm trying to evaluate my velocity at a time instant t plus capital T, which is same as A of t plus capital T. The argument I'm just changing from t to t plus t. Similarly, A of t plus capital T, X on the right hand side is t of capital T. Okay. Now, what is so special about this? Because A of t plus capital T is A of t itself, because it is periodic. Okay. So, which necessarily means if X of t is a solution of the differential equation, then X of t plus capital T is also a solution. Okay. What is so special about it? I think what is it really relevant? Do check it out. If you just take a simple oscillator, simple harmonic oscillator, take a particular solution, and then try to impose it on your solution one, I mean, on your equation also. Just try to verify if it in fact satisfies. Okay, so I mean, this is what the basic premise is about. Okay, if x of t is a solution, then x of t plus capital T is also a solution of this particular dynamical system. Okay, now consider a fundamental solution matrix. Okay, what do I mean by fundamental solution matrix? It is in fact a solution matrix which has columns which are linearly independent solution vectors. Okay, going back to the idea of, let's say, linear systems. Okay, so whenever you talk about a linear system, you did have n eigenvectors. Okay, so n of these eigenvectors, if you just put it together in column format, okay, so what really happens is you do have a modal matrix. Okay, so obviously those are linearly independent solution vectors, and they form the basis for your problem. Okay, now in this particular case, when I do have my coefficient which is in fact not constant but it is in fact time varying, how do I find this? We may have to in fact solve it numerically. We will see how we do that. Okay, but let's presume that I do have a solution, fundamental solution matrix, which is in fact x of capital T, I mean x of t over here. It is in fact a solution matrix, and I do have got this particular solution in this form. Okay, so now, and they form, because this is an independent solution matrix, they form a basis, and any solution can be expressed as a linear combination of this, all these solutions over here. Okay, so this is capital X of t, and I'm just multiplying that with a non-singular matrix, constant matrix over here. Then if I just do multiply this over here, then y of t would also be a solution correspondingly. Okay, so if in case I do have a fundamental solution matrix, a fundamental solution matrix would look something like this. Let's say that this is x of t is a column. Let's say that this is x1 of t, x11 of t, x12 of t, x1n of t. Similarly, this is first column, x12 of t, or x21 of t, x22 of t, x2n of t. Okay, so I just keep on filling these fundamental solution vectors. Okay, what do they correspond to? I think we will come to that very quickly. Okay, I'm just starting with this particular idea with the linear system background, that instead of the vectors which were in fact constants, I do have vectors which are time varying right now. Okay, and just keep on filling them as columns, and I call it as a fundamental solution matrix. And any constant multiplication, a non-zero, a non-singular constant matrix would also be a solution correspondingly. Okay, that's something that we would use a bit later. From the previous results, it is clear that if x of t is a solution, if x of t is a solution, x of t plus capital T is also a solution, right? So if x of t is a solution, x of t plus capital T is also a solution. So what really happens is, in place of y of t, I will just represent it as x of t plus capital T is x of t into this particular matrix C, which is non-singular. Okay, any solution, any other solution is representable as a fundamental solution matrix into the constant matrix over here, or let's say non-singular constant matrix. So on the left hand side, I just replace it with x of t plus capital T is equal to x of t into C correspondingly. Okay, now this is where we would try to find out what is C. Okay, so C is just found out by just, let's say, I will consider my time t in fact equal to 0. So on the left hand side, it becomes x of capital T. So let me just write it on my screen here. So this is x of t plus capital T is in fact equal to x of t into matrix C over here. Let t is in fact equal to 0. That's the initial point that I'm in fact considering, which implies x of capital T is in fact equal to x of 0 into C. Okay, so that's the matrix that I have in fact got. Now, how do I find out C over here? C can be just found out by just multiplying this with x of 0 inverse, pre-multiplying x of 0, x of capital T. Okay, so this is my matrix C that I have been in fact able to find out. Okay, usual case, what we tend to do is x of 0, that is in fact a set of initial conditions for each of the fundamental solutions. Okay, we will see what it necessarily means. If I consider that to be an identity matrix, okay, if I consider this to be an identity matrix, what I end up getting is a matrix C, which is in fact equal to x of capital T. Okay, what we mean by that, let's look at it here. So if in case I had x of 0 is in fact something like this, 1 0 0 up till 0 0 1, and so this is 0 0 1, so on and so forth. Okay, what does it necessarily mean is I give first column as an initial condition. Okay, I give first column as an initial condition, and I find out my particular solution. Okay, I find out the solution, then my matrix C would in fact be, for the first one, I will have, let's say, x11 of capital T, x12 of capital T, x13 of capital T, so on and so forth. Okay, now I have just recorded my information here with the first set of initial condition. The first set of initial condition is 1 for the first state variable, zeros for all the other state variables. Now you can ask me, should we always consider x of capital 0 equal to an identity matrix? No, this is not necessary. You could have chosen any other, but it's usually a good practice to use it as identity. You can change it and you would get the same result. There is no issue with that. Only thing that you need to make sure this x of 0 is not a singular, which means you don't consider the same initial condition twice or thrice. Okay, then obviously you would have a problem. You will not get the intended solution over here. Now, this second set, I do the same numerical simulation, numerical integration of this particular equation, dynamical system. I will get 2 1 of capital T, x22 of capital T, x23 of capital T, so on and so forth. I just keep on recording each one of them. How many set of initial conditions do I require here? N set of initial conditions. Okay, each one of them is only one state variable is unity, and all the others are zeros correspondingly. Okay, I would just have chosen it in this particular format. Any other initial condition would really work. But this matrix C at the end of it happens to be x of capital T correspondingly. Okay, so that's as simple as that. Now, if we just substitute it back into our original equation, T plus capital T is x of T into x of capital T. Quite an interesting result at the end of it, right? So if we have chosen our initial condition, set of initial conditions to be an identity matrix, I would be able to write it in this particular form. Now, what happens if it is x of t plus 2t? So this was nothing but x of t plus capital T into x of capital T. Is that right? Okay, I just increased one time duration here of the time period in this particular case. So t, in place of t, I have just replaced it with t plus capital T. That's exactly what I get. Okay, so that is nothing but if I just substitute it back over here, that becomes x of t into x of capital T whole square. So similarly, if I just do this iteratively, so what I end up getting is x of t into x of capital T power n. Okay, so that's exactly what I would be able to write over here. Okay, now if I just consider my t to be in fact equal to 0, obviously if you just see what is really happening, depending on the characteristics of your matrix C over here, I would be able to say my solutions are growing unbounded or they would stay bounded. Okay, so the matrix C is in fact what is, I mean, we usually do a simple similarity transformation over here, but not really so. I think this is something that we can in fact leave with, no issues with that. So what is really happening? You do find out this particular matrix over here corresponding to fundamental solutions corresponding to each of these column vectors of initial conditions, and the eigenvalues of that particular matrix would tell me if the solution would grow bounded or unbounded. Okay, that's the basic idea that we are in fact getting over here. And when we look into the Floquet multipliers, this is what is called the Floquet multipliers, because we did a simple transformation here, similarity transformation. I think I will not go through very specific detail here. Why? Because I believe some of you might be aware of it. But I thought this would be a very interesting proposition, or the look at the same problem rather than making it quite complicated. It makes it quite simple to look at the response at the multiples of capital T, or let's say the time period of your excitation or time period of your coefficient over here. Okay, so let me just show a very simple numerical simulation over here. How do we find out let's consider a simple van der Pol oscillator. Okay, so what I have done here, I have considered a van der Pol oscillator, and for the van der Pol oscillator, I have created the corresponding variational equation over here. Okay, so this is the vector field that I have written. This is the variational equation that I have in fact considered. Let me just point out here. Okay, so the van der Pol oscillator, if you remember it right, y double dot plus y minus minus epsilon times 1 minus y square into y dot is in fact equal to 0. That's the van der Pol oscillator. Okay, so that is in fact being considered in this particular case over here. So if you just look back at the variational equation that we created previously. Okay, so let me just go back here, the variational equation. Okay, so phi in this particular case, let me just call this as 2 times sine of t. Okay, so that's a periodic solution that you would in fact see in this particular case. So it has a periodic oscillation of amplitude 2. Okay, so if I remember it right, it has a periodic solution of amplitude 2 in this particular case. So let's consider that as our periodic solution. Now, if you look at the variational equation, so it would in fact be del f del y, so which is in fact, let me write down f of y comma y dot. Y comma y dot is in fact y minus epsilon times 1 minus y square into y dot. So del f del y is in fact 1 minus epsilon times 1 minus 2y into y dot. Del f del y dot is minus epsilon times 1 minus y square. Okay. So if this is phi dot would be 2 times cosine of t. Okay. So that's a simple. Okay. I think
The MATLAB.
my iPad is not. Sure. I have written it on the iPad. I think I didn't see my screen. Sorry. Okay. So this is the van der Pol oscillator, and the periodic solution that we are in fact talking about is represented as phi of t, which is 2 times sine of t. We will verify that if it is a periodic solution. I'm assuming that you are aware of that. So f of y comma y dot is y minus epsilon times 1 minus y square in the same format that I have used here. Okay. So my variational equation at the end of it, the linearized version, del f del y is written here, and I just need to substitute del f del y at phi comma phi dot is 1 minus epsilon times 1 minus 4 times sine t. Okay, so this is y, this is 2 times y into y dot is 2 times cosine of t. Similarly for del f del y dot at phi comma phi dot, a similar way. Okay. Now let me just go back to my MATLAB. That's exactly what I have substituted here. Hope I have not messed up anything here. Okay. If in case there is something, maybe I may have to check. Okay. I hope not. Okay. Now this is the equation that I have got, of which I need to consider two sets of initial conditions. One of the initial condition. So because let me just call this as x of 0, the matrix 1 0 0 1. Okay, I'm just writing this vertical line on my iPad just to show that I do have two initial conditions to be considered. Okay, over here on my screen in this particular case, I vary my index I from 1 to 2 because I do have 2 cross 2 matrix over here, and I do consider V0 to be the set of initial condition. I always initialize it to 0. Then I consider in the first case V0. Okay, sorry, I think this makes it a bit more difficult. Okay, let's V0 of 1 equal to 1, V0 of 2 equal to 0, the first case, and V0 of 1 equal to 0, V0 of 2 equal to 1. So those are the two initial conditions. I go about doing this integration. Now, what would be the corresponding time period that I need to consider? If you just look at this particular case, there is a sine t into cosine of t. So there is a multiplication of these two terms. Okay, the time period would in fact be pi for me. Capital T in this particular case is pi. Okay, why? Just because there is a multiplication of sine t and cosine t in the second case also. So whenever you consider this to be minus epsilon into 1 minus y square, that is in fact 4 sine square t. Okay, sine square t, obviously that would be cosine 2t correspondingly minus 1 with the sine correspondingly. So the time period corresponding here, cosine of 2t equal to 1 minus 2 sine square t. Okay, so my time period that I need to consider at which I need to find out my matrix C happens to be equal to pi correspondingly. Okay, I do this integration and pick up the values at only those time instants. Only one time instant is just sufficient. You need to integrate not the whole time duration, only at that specific, only up till that particular time instant, not beyond that. Okay, you don't have to do anything of that kind. Okay, so that would end up giving me the corresponding C matrix. I start with one initial condition 1 0 I get the first vector, I just save it. I do have the second initial condition, I get the second vector, I just put it in the 2 columns. That becomes the matrix C, and I would want to find out what is the corresponding eigenvalues of that. Okay, I did a similarity transformation later, but not we don't have to worry about that right now. Let's look at what really happens. If epsilon is in fact equal to 0, epsilon is in fact the damping coefficient over here. Okay, if epsilon is in fact equal to 0, I do have a simple harmonic oscillator. Okay, a simple harmonic oscillator, what should the Floquet multipliers be like? The Floquet multipliers in this particular case, just remember that we are not talking about these multipliers to be in fact equal to positive or negative. In fact, because we do have a power over here, okay, so the multipliers has to be greater than modulus greater than unity or less than unity is what we are in fact looking into. Okay, because it is in powers that we are talking about, we don't have to worry about is it positive or negative. The multipliers, the eigenvalues of this particular C matrix, if it has a magnitude which is in fact low, which is in fact, let's say this is C, and find eigenvalues of C. Lambda less than 1 implies stable solutions. Lambda greater than 1 implies unstable solutions. I'm talking about modulus because the Floquet multipliers, or let's say these eigenvalues, could be complex also. Equal to 1 implies periodic solution. Okay, so that's a simple way of looking at it. Now, if you just look at epsilon is in fact equal to 0, what I end up getting is the Floquet multipliers, or let's say the eigenvalues over here, happens to be in fact equal to 1. Okay, 0.9999 whatever. Okay, you necessarily mean the solutions are in fact periodic in nature. Okay, so they are periodic oscillations, they don't converge, they don't diverge, they would stay where they are. Okay, the distance from that particular periodic solution, the perturbation that you have provided remains same, it keeps oscillating. Okay, it wouldn't grow with time. Now let's make epsilon equal to 0.1. Okay, we already know in a van der Pol oscillator, the limit cycle oscillation is in fact stable. Okay, now let's look at what the Floquet multipliers are, or let's say the eigenvalues. Here, what happens is one of the multiplier, one of the eigenvalue is less than unity. Okay, the other one is very close to unity. This is because of the numerical accuracy that we have got over here. It doesn't, I mean, don't worry about these numbers. It is 1.000109 or something. The other one is in fact less than unity. So what really happens is it is in fact a stable limit cycle. For a van der Pol oscillator, it's stable limit cycle, which we already know of. Okay. Now let's make it negative. What really happens? Let's see that over here. If it is negative, I need to get one of the eigenvalue to be greater than unity. I'm taking the absolute value here. It has to be greater than unity. Let's verify that. Okay, if it works or if it fails our testing. Okay, good. So you see one of them is very close to unity, 99989. So that's in fact almost equal to unity. The other one is greater than unity. So that ends up being in fact an unstable limit cycle. What happens in an unstable limit cycle? I think I'm running out of time. So let me just put it across here. It's a limit cycle, and any initial condition, if I start here, it would just grow away. So limit cycles can in fact be epsilon is less than 0 is what I'm considering in this case. Okay, so limit cycles need not always be stable. Okay, they can be unstable limit cycles also. Okay, obviously this would in fact go down to the equilibrium point here, and the other one goes to infinity. Okay, I think we will stop at this point. I had few other things, but I don't think we will have time for doing that. Wanted to show some examples, but not sure if we will be able to do that. So what we'll do, if we come after we come back at 2:45, we'll directly go to the idea of bifurcation theory. Maybe I'll take about 45 minutes of that, and let's see if we can come to the aspect of center manifolds and wave propagation theory. Okay, I think I ran much slower than what I thought. Sorry for that. Okay.